this computer. Okay, and there is a momentum of the particle, and it's related to the force acting on it. So this has to be a force that acts on the particle by the second law of mechanics, and this is equal to minus E times electric field plus V K cross B. So this is a semi-classic equation of motion, says that the motion of each and every particle is governed by semi-classic equation of motions, and there is an occupation of the phase space that is given, and this equation describes how it evolves. So this is correct in the absence of now on I would call collisions. So pitch to change this equation. So far the equation was the full derivative with respect to time was 0, which means that the probability is conserved, or the number of the particles in the evolves, and it's locally conserved. So I can look at the small volume in the phase space, and as time proceeds, this volume is getting distorted, but the particles do not disappear from this closed unit element. Now, all this is correct, provided I'm allowed to look at the particle evolution semi-classically. So if the particles would be classical particles, that would be indeed the case. Now, the claim is that, well, this description holds for the length scale R, which are much greater than the wavelengths. Something is fundamentally different if I focus on a short length scale. So let's consider, for example, the case where I put an impurity to the metal. So imagine there is a small impurity, which is an external atom placed in the metal. And so the electron, which is a particle, approaches this external impurity, moves according to the laws of evolution, and then there is a scattering process. Scattering of an electron of this impurity. So electron scatters. Now, so this is a typical scattering problem that you studied in quantum mechanics, so you all know what happens there. This is not something that you can treat classically. So there is for us, impurity is essentially a box. And what happens inside this box is a quantum mechanical process of quantum mechanical scattering. So we can, roughly speaking, separate the semi-classical evolution that took place on a long time scales and something that happens within this box of a size lambda Fermi, or a size which is a characteristic size of the impurity. And what happens within this box is fundamentally random stochastic process. It's a process of scattering in quantum mechanics, and we know that in quantum mechanics, if particle scatters, it can go with certain probability into some direction and may go with another probability in another direction. But what is important that this is a stochastic process. And what happens as a result of this stochastic process, that electron that comes into the system with the state K, after the scattering, may acquire a totally different momentum. And though, of course, the total number of particles is conserved, the statement that df, the full derivative of the distribution function is equal to 0 is no longer true. So the number of particles in the phase in the phase volume in the unit cell is changed. And the equation now reads Tf over Dt plus V gradient Rf plus, well, that's the force that acts on the particles acting on F. And all this is no longer equal to 0, but it's equal to the change of number of particles due to collisions. And by collisions, I mean these type of events that occur at a very short length scales, such as a scattering of impurity. So what I will do now on, for today's lecture, I will only consider this type of scattering between electron and static impurities. And we will analyze how this changes the physical property of the system. So just before I continue, let me make a short break and check with Eitan that things are not dramatically bad there. אוקיי, אבל זה לא, אנחנו לא יכולים, תשמע, זה לא, אין לנו מה לעשות עם זה, מה שאנחנו יכולים לעשות, זה לענות לשאלות שלי שהתחילו. אם אנחנו יודעים שהמערכת הזאת גרועה, זה לא up to us.
אז אני עונה להם, מי ששואל.
אתה עונה על שאלות שאנשים שואלים. אני לא בחרתי את המערכת הזאת, אני הזהרתי ואמרתי מראש שהולכת להיות קטסטרופה. Okay, sorry guys. Okay, so let's go back and repeat the logic. So we separate the problem into two parts. An evolution of a particle, a semi-classical evolution of the particle under the action of external forces. And this is accounted by Liouville operator, and something that happens on a very short time scales, very short spatial scales and also time scales, which we call collision. And we would not try to describe the physics there. We'll consider this as a black box. It's a black box, and we will characterize it by certain scattering probability. So what do I mean by that? So let us remind us, what do we study? What have we learned about normal quantum mechanics 1 scattering problem? So we have some scattering potential V of R. We solve a scattering problem, compute scattering.
I have a question. In the last lecture, you told us there are, at the end of the lecture, you told us there are 3 types of interactions: coulombs, electron-electron, electron-phonon, and disorder.
Correct.
And you said we are going to do the disorder.
That's what they're doing. So now it's a disorder.
No, now it's a disorder of the electron.
Say it again.
Now it's the electron-electron interaction?
No, now it's a disorder.
And by disorder, you mean interaction with imperfections of the lattice?
Correct.
Okay, thank you.
So yeah, so I will consider three prototypical types of collision integral, like I said last time: disorder, electron-phonon, and electron-electron. In principle, there are many more, but these 3 are especially important, and they each of them is kind of prototypical one. So they're important paradigms for understanding transport. So I'll focus on these 3 on these 3s, and today I'm talking about disorder, static disorder. So static disorder is essentially a collection of randomness, of random impurities. And if you go into real experiments, you will learn that there are certain types of disorder, of static disorder, that that occur in the system. And right now, it's for us, it's not very important. For us, disorder, it's some external potential V of R, which we'll call an impurity. So yeah, so I will consider V of R. So crystal is a periodic, ideal periodic potential. Okay, so maybe I should remind the logic. So we started with a problem which we called a crystal. And so we had a potential U of R, which was periodic. We solved the Schrödinger equation, and we find a solution which are n, k of R, and they're called Bloch functions. They're functions of this periodic potential. Now imagine that on top of this periodic potential, there is an extra potential V of R, which is not periodic. It may come as a result of dislocation of an atom, of a charge impurity. There are many realizations in the experiment that create such an additional potential in the lattice. But this is a violation of the crystal periodicity in some way or another. So we will consider this potential a static disorder or an impurity. Okay, so now.
So there is a localized place where there is an additional potential which is not periodic.
Yes, there is a localized confined in space potential which is not periodic. For us, this is definition of a static disorder. So this is a model of an impurity. Now, physical realizations, it may be that it's an extra ion, and in this case, this impurity will be a charged ion with a Coulomb potential. So it means that this potential V of R will have power long tails. It can be a neutral atom. In this case, this will be a short range potential. These are details that are important for interpreting this or that experiment. However, right now it's not terribly important. So we have this potential V of R, and for us now it's a scattering problem in quantum mechanics. We want to extract the minimal information that is needed for incorporating this potential into the Boltzmann equation. And the information we will need is so-called scattering probability. The scattering probability for electrons that comes into the potential with the wave vector k to scatter into the state k prime. And using Fermi golden rule approximation, this thing is just 2 pi over h bar, number of impurities, delta function of epsilon k minus epsilon k prime times matrix element between state k, potential, and state k prime. All these squared. So this is what's called Born approximation. First Born approximation. And this thing is called Fermi golden rule. So Fermi golden rule tells us that if you have a single impurity, that the scattering is restricted to the energy shell. So this delta function means that the energy cannot be changed in the process of elastic scattering. Static impurity does not change the energy of the electron. This is the scattering amplitude, absolute value square, and Ni is the concentration. Ni is a concentration of the impurities. So this is a building block of our theory. It has nothing to do with the remaining part of Boltzmann equation. We just solve quantum mechanic 101 scattering problem. We take a potential, we study the scattering of this potential, and the easiest way to do it is by using, say, Born approximation. You don't have to use a Born approximation, of course. What this thing really is just a scattering cross-section that we have computed within Born approximation.
What is the approximation itself?
It's a Born approximation.
But where did you use it? What is the thinking of the approximation? The entire equation is the Fermi golden rule, but where is the approximation?
Okay. Let me try to be more careful with this word. So a sec. How should I say it? Second. Okay. So we need to compute W, K to K prime. This is the transition probability. What it means that if you send an electron, so this is a single particle problem. If you send a quantum mechanical particle, an electron, with the state K, and it scatters of the potential K prime. They're solving scattering problem. Scattering problem is described by scattering matrix or T matrix or whatever you like it. Now, when you compute T matrix for states K and K prime, you can employ different approximations. The easiest one is the perturbation theory for small impurities. So if you have an impurity of size A, and this size is much smaller than the wave vector of the wavelengths of the electron, then you just do a perturbation theory and you say this is the amplitude of my impurity U. Then the scattering matrix is roughly speaking proportional to the Fourier transform of the potential at the wave vector K minus K prime. This is what is called first Born approximation to the T matrix. Something that is supposed to be studied within the quantum mechanics one. This statement is an approximation, and this assumes that A over lambda Fermi is much smaller than 1. This condition is frequently enough, not always. So this typically is sufficient when the impurities are weak and small in sizes. So size of the impurity is much smaller than lambda Fermi, and the potential U is much smaller than the typical energy of the electron. It's called Born approximation. Are we on the same page? Or I need to remind you?
I try to remind it by myself and see if I understand. Thank you.
Well, what I'm trying to say probably that generally speaking, what stays here for the transition between state K and K prime is number of impurities times cross section differential cross section for the state K and K prime times energy conservation. And this cross section can be computed with various accuracy depending on whether the potential of impurity is strong or weak. So essentially you're doing a perturbation theory in the impurity strands, normal scattering theory in quantum mechanics. And this allows you to compute the scattering amplitude and the scattering probability, which we call WKK prime. So this object has a very simple classical sense. If you send electron in a state K, what is the probability to find it after the scattering in the state K prime? Okay, so if you don't remember, just open scattering theory, a chapter in any textbook on quantum mechanics, and you will find it there. Okay, so now the next statement is that the only building block that we need to compute from the quantum mechanics theory is this scattering probability. So this is something that characterizes a single impurity. You compute it within quantum mechanics. Once you have it, we can formulate, we can derive the collision integral and have the Boltzmann equation for this case. So now we need to compute the collision integral, the right-hand side of the Boltzmann equation. So once again, df over dt plus v k grad rf plus r dot grad k f is equal to df over dt collision, also denoted by collision integral of f. And this is the object that describes how many particles are coming in or leaving state K and R as a result of collisions. So imagine that we have a phase space picture. There is a cell in the phase space that we call K and R. So it's a cell in the phase space. And due to the evolution operators, particles move in the phase space, but don't perform any abrupt jumps. But there is a term which we call collision integral that causes particles to disappear from this cell or to appear in this cell as a result of some collision which is occurring far, far away in the phase space. So in completely different part of the phase space, there is another cell, and electrons, as a result of scattering, electrons jump from one point in the phase space to another point in the phase space. And this is something fundamentally different from what we had so far. And this was ingenious contribution of Ludwig Boltzmann, who developed this field. and formulated one of the most famous equations in physics. So now I'm going to write the collision integral for static impurities and try to explain its meaning. So for the process above, the collision integral looks like sum over k prime over all points in the momentum space, w k prime k f k prime 1 minus fk minus w k k prime fk 1 minus fk prime. And these two terms I can symbolically call the first one influx and another one to call an outflux. Okay, so let us see if we understand what is written here. So let us look at these two building blocks, and as you see, they are coming with opposite signs. So what is the meaning of the first building block? So it has the following terms. So the term 1 minus fk says this is the probability that state k is empty. F of k prime is a probability that state k prime is occupied. And wk prime is the probability to scatter from the state k to the state k prime. Sorry, from the state k prime to the state k. So all these things together is a product of three independent probabilities. Probability to find state k empty, probability f of k prime to find the state k prime occupied, and the probability of transition from state k to state k prime. So all these together is a probability of transition between state k prime to state k. And there is a summation of all possible states k prime. So all these together is the number of electrons that scatter into state k from the entire universe, so to say. Therefore, this is an incoming current. So this is the current in the phase space, and this is a total incoming current into the state k. So did you follow the logic and explanation of what these terms mean? Okay, I see that some people did. Now let us look at the second term. And now I can repeat the same story once again, replacing ports k and k prime and empty with occupied. So this is the probability to have state k occupied. This is the probability to have state k prime empty. And this is the probability of transition from k to k prime. So all these together, sum over k prime, it's an outgoing current from the state k to the entire universe. So the physical picture is the following. So there is a cell k, And as a result of collision, these electrons leave this cell into other states, and electrons are coming into this cell from all other states. So this will be an outgoing current, and this will be an incoming current in the phase space. These processes are described by these random collisions. And okay, so what else should we say about these collision integrals? So, okay, so probably you see it very clear from here that this integral is written for fermions, because 1 minus f structures imply Fermi statistics. Yeah? So the reason why we are writing 1 minus f, because these particles are fermions, and we cannot have more than one fermion inside the cell. So if state is occupied, f is equal to 1, 1 minus f is equal to 0. So there is no incoming current into the state which is already filled. And the same goes for an outgoing current. You cannot scatter into the states that are occupied. These are fermions, and you cannot go to the state which is occupied. Of course, I'm writing the most simple version of this story. There are enrichments and complications. You can account for spin, and then the states would be spinful. But in the simplest possible way, this is the structure of the collision integral between electrons and the static disorder. Now let us take this structure and use it to compute some basic features of the system. Let us compute, say, electric conductivity. Okay, so this is the simplest level of understanding the transport properties of metals. Let us compute electric conductivity on the level of the Boltzmann equation. So we have an equation. Let us see how we can use it to compute electric conductivity. Okay, so first of all, let us make some, no, we don't need to. So let us look at the Boltzmann equation once again. So df over dt plus v grad f minus e times e grad k is equal to minus integral over k prime, and this all long sum that we just learned, k prime fk 1 minus fk prime minus wk prime k fk prime 1 minus fk. And let us assume for simplicity that the magnetic field is 0. No magnetic field. Just to start.
You forgot the F in the first line.
Thank you. Okay. So magnetic field is 0. And we want to compute electric current. So that's our equation. What is the current of electrons under the influence of external electric field? So there is a piece of metal. We apply a constant electric field connected to the circuit. This is the circuit. We measure the current. What is the current if we have a piece of metal with some disorder in it? What would be the electric conductivity? And of course, we all know the story. We anticipate the Drude conductivity, but now we will get it systematically from the collision integral as the simplest exercise. And let us assume that the electric field is static. So it's, of course, it's a strictly speaking, a function of omega and q, but let's assume that the field is static, so frequency is equal to 0, and q goes to 0. So a constant in space and time electric field. A DC limit, DC electric field. Okay? So can we solve the equation in this case? And my statement is yes. So first of all, because it's a DC problem, we can neglect the time derivative. Then, because it's a DC problem, there is no R dependence, and we can neglect this term as well. And to make life even easier, let us assume that WK K prime is equal to WK prime K, which means that the probability to scatter between state K and state K prime, it's the same as the probability to scatter from state K prime to K. This is not necessarily the case, but for most scattering processes, it is, and for what we are discussing right now, that's sufficient. So in this case, what we are left with is the equation minus E times electric field, gradient in the K space acting on distribution function is equal to the sum over K prime W K K prime, and what is left there is Fk minus F of K prime. So this is the simplification of the Boltzmann equation. Okay, now what we will assume that we want to be in the linear response. Linear response. So which means that electric field is very weak. So we're applying a small electric field. And we'll be interested in the small current that is a response to this electric field. In other words, we are computing linear transport coefficients. Then we can solve this equation using a perturbation theory in electric field. So how do we do it? We say that distribution function in the presence of electric field is essentially an equilibrium distribution function, Fermi-Dirac distribution function that we discussed last time, plus a small correction. This is the corrections due to electric field. So we expect delta F to be proportional to the applied electric field. In the absence of electric field, the distribution function goes back to the Fermi-Dirac distribution function. Okay. So then we look at the Boltzmann equation and we realize two things. Thing number one, the left-hand side is already proportional to the electric field in the power 1. So there's an electric field here. So which means that if we want to keep the lowest terms in the electric field, we can approximate the function here by Fermi-Dirac part and neglect the correction delta F there, because these terms will be proportional to the electric field square. That's the statement number one. Did you follow this statement? Good. Statement number 2, which is less trivial and is very important, and it has to do with some fundamental properties of the collision integral. If we will substitute into the right side of the Boltzmann equation f Fermi Dirac as a function of k, of epsilon k, into these guys and into that guy, the collision integral will vanish. Well, it's very easy to see. So let me just take this thing and look into that. So we have W k prime times f Fermi Dirac of k plus delta f of k minus f Fermi Dirac of k prime minus delta f of k prime. Now let me group these terms. So it'll be part wk k prime, and there's a big piece, f Fermi Dirac of epsilon k minus f Fermi Dirac of epsilon k prime. I'm sorry, just yeah. Yeah. But you can translate them just translate them, yeah. Plus delta f of k minus delta f of k prime. And we assume that delta f is much smaller than f. So these are small corrections. Now note what happens here. Wk k prime is a transition probability between states k and k prime. And as we saw before, Wk k prime is proportional to the delta function of epsilon k minus epsilon k prime. So in words, it means that the energy is conserved in the process of elastic collision. So if you send an electron on the energy shell epsilon k, out goes an electron on the same energy shell. That's because the impurity is static. That's because the energy is conserved. So it means that the energy Ek must be the same as energy of Ek prime. So which means that these two terms are gone. And we are left with the equation where here only the small part of the distribution function remains. So on the left-hand side, there is a known function, which is a derivative of Fermi-Dirac function with respect to k. And on the right side of the equation is an unknown function delta f, which is a correction to the equilibrium distribution. And now we need to solve this equation and to find delta f. Okay, so if this is clear, then let's try to analyze this equation. And
if you say f is about the Fermi-Dirac distribution, can't you say the delta f is the derivative?
Delta f, almost. We want to say that the delta f of k will be a derivative of Fermi-Dirac function with respect to energy times a function that depends on the direction of k. But we are jumping a little bit ahead of ourselves. So what we see from here is an integral equation. Yeah. So strictly speaking, what we got is an integral equation. There is a left-hand side of this equation which is known, and the right-hand side of this equation is an integral equation in the unknown function delta f. That we need to find. Now, how are we going to solve this equation? That's the next story. Okay, so let us look at the left-hand side of this equation. What's really staying there? It's a derivative of Fermi-Dirac distribution function. If you remember, Fermi-Dirac distribution function, epsilon k, it's 1 over epsilon for energy epsilon k minus nu divided by temperature plus 1. So this is a function that depends only on the energy and has the following structure. It's 1, then it goes to 0. There's a position of a chemical potential, and there is a strip of the with temperature where this function is not equal to 0, 1. So if you try to differentiate this function, if we differentiate function f, then the derivative of the function with respect to k will be the derivative of this function with respect to epsilon times the derivative of epsilon k with respect to k. Now the derivative of epsilon k with respect to k is of course just the velocity. So we are getting velocity times df over d epsilon. Now look at it. So this is the function f Fermi-Dirac that you differentiate with respect to epsilon. So the derivative is obviously 0 all the way up to here. Then it goes up and then it goes down again. So the derivative of this function is different from 0 only in the stripe of the width temperature near the chemical potential. Therefore, the left side of this equation, if I now look at it, what the left side of this equation is, it's just E times electric field times velocity in the direction of k, df Fermi-Dirac over d epsilon k, and this is something restricted to the chemical potential. And it's equal to the sum over k prime, wk k prime, delta fk minus delta fk prime. And like I said, this thing on the left is only different from 0 at the close vicinity of the chemical potential. So it means that far from the chemical potential, the electrons are at equilibrium and delta F is 0. Close beneath the chemical potential, all states are occupied and electrons are at equilibrium as well. However, in the vicinity of the chemical potential, in the close vicinity of the Witts temperature, there is something interesting going on. And this is something that we need to compute. Okay, that's why once we realized that things will be only different from zero in the vicinity of the chemical potential, we are looking for the following solution of this equation. So some function that is also restricted to the vicinity of the chemical potential times some unknown function f of k that depends on the angle. So we substitute this into the Boltzmann equation, and just for simplicity, let me now replace sum over k prime by the integral over dk prime. And let me focus on d equal to two-dimensional case just to make my integral simpler. Later on, we can correct and allow for all other dimensions. So in this case, what I'm getting is minus E times electric field times velocity in the direction k is equal to the integral over d k prime, two-dimensional integral, f of phi minus f of f prime times w for the angle phi minus phi prime. Okay. Now, what I'm saying is that there is a direction parallel to E. There is a momentum K. There is an angle phi between the direction of the vector on a two-dimensional plane and the vector E. And the scattering probability between state K and the state K prime is proportional to the function that depends on the angle between these two vectors. So this implies that I have a Fermi surface which is just a sphere. Epsilon k is equal to k squared over 2m. And then I have a vector k prime on the same sphere. Maybe I should draw it there. Vector k prime. They all lie on the Fermi surface. This guy has an angle for phi. That has an angle phi tau. And then the scattering probability between state k and k prime depends on the angle between these two vectors. Okay. So this is my equation. And in these notations, it means minus E times electric field. Minus E times electric field times Vk times cosinus phi is equal to the integral over d to k prime f of phi minus f of phi prime w k between phi and phi prime. Now I want to rewrite sorry. And yeah, and k prime runs of course on the shell epsilon k prime is equal to epsilon k. Okay, I can integrate with respect to the absolute value of this thing, so it becomes E times Vk cosinus phi is equal to the density of states integral over d v prime over 2 pi f of phi minus f of phi prime times w phi minus phi prime. Now, how do I solve this equation? So this is still a non-trivial equation, but there is a simple ansatz that solves this equation. So f of phi, I'm looking at it and I'm saying, let me look at the solution that looks E cosine phi times tau transport, whatever that means.
I didn't understand what did you write in the integral, the d psi tag on over what? What is the denominator?
2 pi. And now I plug this thing into this equation. So I'm getting minus EE Vk. Minus EE Vk cosinus phi. It's equal to the density of states integral over d phi prime over 2 pi f of phi, f of phi we already decided to call E V K tau transport times cosinus phi bar cosinus phi, my mistake, cosinus phi minus cosinus phi tag times w phi minus phi tag. And now we can cancel EE and V. And I'm having an equation cosine phi is equal to nu tau transport integral over d phi r over 2 pi cosine phi minus cosine phi tag times w phi minus phi tag. Okay, just bear with me one more minute and then I'll explain what actually is going on physics-wise. But formally we got this equation, then we can shift the variables of integration. So let's call phi tag to be equal to phi plus phi double tag and use an equation that cosine phi plus phi tag is equal to cosine phi tag plus minus sine phi tag. Then I plug this into the equation above, and I'm getting that all this thing is equal to mu integral over d phi over 2 pi w k of phi 1 minus cosine phi times tau. Times, okay, so let's call this cosine phi, times cosine phi. So cosine phi is cancelled, and I'm getting 1 over tau transport is equal to nu integral over d phi r over 2 pi w k phi 1 minus cosine. Okay. So we found that delta f of k is equal to minus df0 over d epsilon cosine phi tau transport when tau transport is given by this integral. Now, what does this integral tell us? It tells us that there is a time, characteristic time, associated with the scattering probability W. If scattering probability Wk does not depend on scattering angle, it means that so-called S-wave scattering, electron comes into the system and scatters in all directions with the same probability, then in this case, 1 over tau transport becomes mu integral over d phi prime over 2 pi wk. So it is just mu times w. If, on the other hand, wk very strongly depend on the scattering angle, say it prefers small angles, then phi bar are very small, so we can expand cosine, and you see that these brackets are almost identically 0. So what does this show? So the physical picture is very simple. So imagine that there are impurities, and there is an electron goes and scatters of these impurities. So there is a typical time, which we call tau, which is a scattering time. So this is just how frequent electron hits an impurity. So if there are impurities that typical distance between the impurities is some L0, an electron moves with the Fermi velocity v Fermi, then the time it takes between individual scattering is just the distance between the impurity divided by the velocity of the electron. And this time will be precisely this equation, but without the cosine term. So you have a scattering probability W to scatter at some angle phi. You integrate it over all angles, and you get the typical scattering type, how frequent electrons scatter off the impurities. Now, what we find in this formula, it's so-called scattering time. So we see that it's not just one, it's 1 minus cosine phi. And what this shows that if, imagine that you have an electron that goes with the momentum k and scatters of the impurity, but only by tiny amount such that the momentum after the scattering points into the direction which is similar to the direction of the incoming momentum. This is so-called small angle scattering. So there is a scattering event. It happens every tau, but the change of the momentum in the process of individual scattering event is rather small. So the typical angle in the scattering process changes, but the change is much smaller than 2 pi. Then it would take many scattering events before the momentum of the particle equilibrates. So roughly speaking, in this case, you can think about equilibration of the momentum that occurs as a result of many scattering events. And therefore, the time at which momentum equilibrates, momentum of the electron randomizes, is much longer than the time between individual scattering. So this 1 minus cosine is precisely about that story. So if the scattering probability is angle independent, which means you more or less randomly scatter into all possible directions, then you can forget about this cosine, or mathematically the cosine averages to 0, and tau transport and the scattering time are the same. If, on the other hand, the scattering probability W as a function of angle is preferentially as a maximum at small angles, then cosine makes a big difference and the transport time is much longer than the scattering time. And what this integral equation tells us is precisely this. Okay, so we have solved this integral equation. We found the correction to the distribution function. So we know that our correction to the distribution functions as a result of competition between driving electric field and impurity scattering is equal to minus E times V. So we decided to call this E times V times cosine angle between these two creatures, and some object we have computed, and it's just a constant. We computed this constant. It's a complicated constant, but nevertheless, we have found that it's given to the density of states, averaging over all angles, scattering probability as the function of angle, and 1 minus cosinus phi. So these two things is what we need. Now we can compute electric conductivity. So how we compute electric conductivity? The way we have learned to do it before, we compute electric current. So we integrate over all momenta, electric charge, velocity of the electron, and how many electrons are in this state. Now, once again, how many electrons in the states has two parts in it. One is the Fermi-Dirac part, and another part is delta F that we have just computed. So in principle, I need to substitute both terms. However, you probably see that Fermi-Dirac part does not give any contribution to the electric current. So that's the statement number one. And therefore we are left with minus E integral over d to k Vk delta F as a function of k. So only the non-equilibrium correction gives a contribution to the electric current. And now we can plug the non-equilibrium correction from the previous formula. And what we get, so we now take this thing and plug it. We take this thing and plug it into here. Well, so what remains is E squared integral over d epsilon k integral over d phi over 2 pi Vk cosine phi df0 over d epsilon E, sorry, you already taken, electric field Vk again, cosine again, and tau transport. And all this becomes E squared tau transport integral over d epsilon k minus df0 over d epsilon Vk square in the direction and cosine phi square averaged over phi. And this is E square density of states V Fermi square over 2 times tau transport. Times, sorry, most important thing, electric field. So what we found is that electric current is proportional.
What is the V? You meant Vk or Vf?
Vf, Fermi velocity. And what we found is that electric current is given by sigma dot E, sorry, not dot, just sigma times E. It's a scalar for this case. And sigma that we found, this is electric conductivity. And what we found, that's equal to E squared times density of states at Fermi energy, V Fermi square over 2 times tau transport. Now a remark about V Fermi versus Vk. So we have an integral with respect to k, something that was called Vk square times df0 over d epsilon k. Now note that this function is different from 0 only for k close to the Fermi surface, right? So if you compute Vk, this will be for parabolic spectrum k divided by m, right? But since we integrated with the function which is very sharp and localized in the vicinity of Fermi surface, this thing is roughly equal to k Fermi divided by m times the direction of the vector k, right? Now, when we look, so essentially we have the following integral: e square integral over d epsilon k times minus df0 over d epsilon k, density of state at epsilon k, vk as a vector in the direction, okay, vk is a vector square divided by the dimensionality of the space 2 times tau transport. Now, this object is practically a derivative of theta function. Yeah? So if temperature is 0, think about limit when temperature is equal to 0. So when temperature is equal to 0, this is essentially the Fermi-Dirac distribution function is essentially a theta function. So the derivative of Fermi-Dirac, okay, we call it Fermi-Dirac function with respect to energy, it's essentially delta function of epsilon k minus epsilon Fermi. So everything in low temperature limit is restricted to the vicinity of the Fermi surface. And therefore, all functions that depend on k smoothly, like density of states, can be replaced by density of states at Fermi surface. And V of k, absolute value of V of k square, which is k square over m square, can be replaced by k Fermi momentum square over m square, which is the same as V Fermi square. So V Fermi is just k Fermi over m. And k Fermi, it's the position where energy lies precisely at the chemical potential. Okay? Okay, people, let's have 10 minutes break and then repeat the same story from a slightly different perspective. Hello?
When to come back?
So let us make 10 minutes break. Let us meet at, I don't know, 70:35. Okay, would it work for you?
When does the lecture finish?
Should be fine.
70, yeah, correct.
And when does the lecture finish?
Okay, I want to look, I don't know how. Are you telling me that that you want us to finish and meet next week? That's also fine.
No, just to know.
I want to repeat. I have 4 more pages which repeat all this story from a slightly different perspective. I want to show you how the same results can be obtained from a different perspective. I think I need like 30 more minutes.
Okay, thank you.
Okay, so let us meet in 10 minutes.
Okay.